Alright, so we're still moving along here. We just wrapped up and compared from example 3, compared our actual distance to the approximation and saw that they were pretty close. So we're going to move on now, take a look at example 4. So this is going to be about a little bit about some economic things. So we got this idea called production level. So what production level is, this is going to be the number of units. So number of units manufactured. So production level is number of units manufactured. And marginal cost is the cost to produce an additional unit. So marginal cost is the cost of producing an additional unit at a production level. At a production level. We get this equation here, which is marginal cost is equal to the cost of 1 unit beyond C naught minus the cost at X naught. So production level X naught, it's basically the cost of a 1 unit increase at a production level of X naught would be your marginal cost. So we're going to look at example 4 here. Now we just got a couple more examples, then that'll wrap up section 3.4. So this is example 4 from the book. We got, so this is cost of a flight. So data suggests the cost of a flight is given by, we'll get C of X for cost equals 0.0005x cubed minus 0.38 x squared plus 120x. X is the number of passengers. So part A. They want us to estimate the marginal cost at 150. So we have 100 people on the flight. How much does it cost to add an additional person? Part B. Compare with the actual cost. And then part C. Is it more expensive to add a person at 150 or 200? Okay. So now what we want to do is solve this. We'll say, all right, to estimate the marginal cost of 150, it's the cost of 151 minus the cost of 150. And we're going to approximate that by the derivative of the cost function at 150. So we're going to approximate the marginal cost by using the derivative. So we're going to do basically use the power rule to calculate this. So we're going to get 3 comes down, it hits the 0.0005. So the derivative is going to be 0.0015 x squared minus, 0.38 times 2. It's going to be 0.76x plus 120. So when we want, what's the c prime of 150? That's going to be about equal to 0.0015 times 150 squared minus 0.76 times 150 plus 120. We're just using this equation right here and replacing the x in it with 150. So we'll see what we get. Alright, so we're stepping in a calculator here. And I get, it's about equal to $39.75. Okay, so I guess that seems alright. So part B wants us to figure out what's the actual cost, and then compare it to part A. So for part B, we want to take this original function here, we want to plug 151 in it, and then subtract 150 from it. So the actual cost, C of 151 minus C of 150, will equal, let me scroll up here so I can see the equation. Basically these x's, I'm going to replace them with 151s, and then replace them with 150s. So it's 5 times 151 to the third minus minus 0.38 times 151 squared plus 120 times 151. And then we're going to subtract from that 0.005 times hang on, 0.0005 times 150 to the third minus 0.38 times 150 squared plus 120 times 150. And we get 39.595, so we'll say 39.60. So we're off by about 15 cents, which says our approximation is pretty decent for what we're doing. And then they say, is it more expensive to add a person at 150 or 200? We have 150 at 39.75. So for part C, I'm going to use this right here again, this equation over here to with 200 plugged in, and that'll get me the marginal cost, or that'll get me an approximation on the marginal cost. So we get 0.0015 of 200 squared minus 0.76 times 200 plus 120. And this is about equal to $28. So we'll say, the way it phrased it, it said, is it more expensive? It's more expensive to add a person at 150. So it is more expensive to add someone at x equals 150 because it costs $39 up there, $39.75 up there, versus the $28 down here. Okay, so we are wrapped up on that one. So now we're going to get, we've got about two more problems we're going to work and then say that's good for section 3.4. So this is example 5. So we got a truck enters the off ramp of a highway at time equals 0. So truck enters off ramp of highway at time equals 0. And we say its position after t seconds. So position after t seconds is given by s of t equals 25t minus 0.3t cubed meters, and this is for t is between 0 and 5. And then part A, we say how fast is the truck going the moment it leaves the off ramp, and is it speeding up or slowing down. So how fast is the truck when it enters the off ramp, and then part B, is it speeding up or slowing down. So basically, to figure out how fast the truck is going when it enters the off ramp, we just take the derivative of the position to get the velocity. So for part A, we want the velocity equation. V of t equals what? Well, the derivative of the position function is the velocity function. So if we take the derivative of this, that is going to equal 25 minus 0.9 t squared. And this is our velocity function. And they want to know what's going on the minute it enters the off-ramp. So what's the velocity at time equals 0? 25 minus 0.9 times 0 squared is 25. And this would be meters per second, I guess. Okay. Part B, are we speeding up or are we slowing down? Well, we can graph our velocity problem, or our velocity function. If we graph it, it's a parabola that's opening downwards and has shifted up 25. So it's 25 up here, and then it is a parabola that kind of opens downwards. So if this is time equals 0, and then we look at kind of the positive times, if this is our starting point and we're looking at times off to the right-hand side, the shape of the graph tells me that all the y values get smaller and smaller and smaller. So this tells me that the truck is slowing down. So I just kind of looked at the graph of the velocity function, and it starts out at 25, and then since it's a parabola opening downwards, it's going to be slowing down. Okay, so that should wrap that one up. And then we got one more, and then we'll say that's it for section 3.4. So for this example, we got a couple of equations. This is going to be the motion under gravity. We have S of t equals S naught plus V naught t minus 1/2 gt squared. So, and we also have V of t. This equals the derivative of the function there with respect to time. So it's the derivative of the position function. This is going to be V naught minus gt. So these are our two equations for motion under the influence of gravity close to the surface of Earth. In these, S naught is initial position. V naught is initial velocity. G is going to equal, let's see, we're going to use 9.8, I think, or we're using 9.81. It's 9.8 meters per second squared. We'll use that for G. That's acceleration due to gravity. And now we're going to put that all together to solve one last equation. So it's going to be example 6 from the book. Last one we're going to do here from section 3.4. So say a stone is shot up vertically. So a stone is shot up vertically with initial velocity of 50 meters per second from an initial height of 10 meters. Okay. Part A wants us to find velocity at t equals 2 and 7. And it wants us to say why are the signs different on those two. Part B wants us to go through and say what's the maximum height. And when does it reach that max height? Okay, so we're going to use, we want to find the velocity at these points, so we're going to use the velocity equation. So for part A, we say the velocity equation is v of t equals v naught minus gt. Initial velocity is 50 and g is 9.8, so we get 50 minus 9.8 times t. That is what we want there. So I'm going to just plug in time equals 2 and time equals 7, and we'll see what we get back. So v of 2 and v of 7. And we're going to use this right here for our v of t equation. So we're just plugging in 2 and 7 for the time. So 50 minus 9.8 times 2 is 30.4. I believe this is meters per second. Yeah, meters per second. And then 50 minus 9.8 times 7 is negative 18.6 meters per second. So the sign, why are the signs different? Well, the signs are different because this first one is the velocity on the way up. So this right here is the stone's moving up, and then this one, the stone is coming back down. So that's why the signs are different on those. One of those is on the way up. At 2 seconds, it's still going on the way up, and then at 7 seconds, it's coming back down. Okay, what is the maximum height? When do we reach the maximum height? So we're going to need our position equation for this one and the velocity equation, I think. So, you know, let's just use the velocity equation first. So you are at, we think of throwing something upwards. At the very top, there'll be a brief moment where it stops, where it's at the maximum height. And so the maximum height is going to be where the velocity is 0. So we're going to set our velocity equation here equal to 0. And we're going to solve it for t. That'll tell us how many seconds. That'll tell us the number of seconds when we're at the maximum height. So this right here is the time that we should be at the maximum height, because that's the time it takes for us to reach a point where it stops for a bit. Then it starts to fall back down. So we're going to use the position function, which the position function is initial position, which is 10, plus initial velocity times t. So our position function is initial position, which is, we shot it from a height of 10, plus the initial velocity times time, minus 1/2 gt squared. So that's minus 1/2 times 9.8 times t squared. And what we're going to do now is we're going to plug in this time right here is going to plug in for both of those, and that'll tell us the maximum height. So S of 5.102, this will be the maximum height. And I just need to use my equation to figure out what that actually is going to be. I think I've got it all typed in right. So I'm getting about 137.551 meters will be the maximum height. And this is the time at the maximum height. Alright, and that should wrap up section 3.4. So stop there.